Hello everyone, I am Aryan Nanda and this is final video presentation of my GSoC project, Enhanced Media Experience with AI-powered commercial detection and replacement. The mentors for this project were Jason Kreidner, Deepak Khatri and Abhishek Kumar. The goal of my GSoC project was to make a system that is capable of detecting commercials from media streams and then accelerate the system using the C7X DSPs and DL accelerators present in BeagleBone AI64. The primary motivation behind this project is to enhance the media consumption experience by providing users with control over the content they see during commercial breaks. By developing a system that detects and replaces commercial in real time, this project aims to ensure that viewers can enjoy a seamless and pleasant viewing experience tailored to their preferences. Now, I'll provide a concise overview of each key phase in my project. We will touch down on the major milestones: dataset collection and feature extraction, dataset pre-processing, model results, input pipeline, real-time pipeline, and accelerated inferencing. I'll give you a bird's eye view of the entire process without getting bogged down in the details. Let's start with dataset collection and feature extraction. Dataset collection was in itself a huge task because videos occupy a lot of space and having a large dataset of videos is not feasible. For projects like Enhanced Media Experience with AI-powered commercial detection and replacement, obtaining comprehensive dataset is crucial. However, acquiring large-scale video dataset, particularly for commercial and non-commercial content, present challenges due to their size and storage requirements. It was my finding in the pre-GSoC period that tells that YouTube 8am dataset stands out as a significant resource for this project. It includes millions of YouTube video IDs with detailed machine-generated annotations across a diverse set of visual entities, including television advertisement, which is particularly relevant here. This dataset includes frame-level features, that is, 1 per second with up to first 360 seconds per video. Videos are stored in TF record files, each file containing 287 videos. Now let's go ahead with dataset pre-processing. After dataset collection and feature extraction, the shape of different features is as shown. Here, the first dimension represents the number of videos whose features are extracted. This is why this is constant for both audio and visual features of the same class, as both belong to same number of videos. For example, 4364 represents the audio and visual features of 4364 videos. The second dimension is the number of frames in each video. The YouTube 8am dataset limits the feature extraction process to the first 300 seconds with 1 frame per second. By this, every video should have 300 frames by 1 per second for 300 seconds. Then why is it variable? This is because the video could also be shorter than 300 seconds. In such a case, the number of frames would be fewer than 300. The third dimension is where the features lie. Corresponding to every frame, there are visual features of length 1024 and audio features of length 128. Next, I merge the audio and visual features and then fix the size of frames to 150. Here you can see I have merged the audio and visual features and they become from 1024 plus 128 to 1152. Now we have got two classes, one of commercial features and another of non-commercial features. Then I fix the size of frames to 150 so that they are not variable and I can easily convert them into a NumPy array. Here you can see the different models I tried so that I could compare them and finally take out the best one. But after verifying the supported layers, I decided to use the CNN model for my commercial detection system. Now one question arises, how CNNs will be able to recognize sequential meaning in a video classification problem. CNNs are typically used for learning spatial patterns, but a problem required understanding sequential meaning. In advertisements, for instance, a sequence often starts with some content and ends with a logo appearing. To capture this sequential aspect, I trained my model on sequences of frames rather than individual frames. Instead of processing each frame independently, I grouped multiple frames together and trained the model on these sets. This approach introduced sequential context, allowing the model to learn from the sequence of frames rather than just one frame at a time. This significantly improved the model's real-time performance. If you find this project interesting and you want to learn more about it, then you can visit my blog's website. Here I have written very detailed blogs on each key phase of my project. Let's go ahead with input pipeline. For the frame level visual features, the entire video frame 1 per second with up to 300 seconds per video was pre-processed with the publicly available Inception network that was originally trained on ImageNet. This reduced dimensionality to 2048 features per frame and pulled motion out of video, in essence making it a still video. PCA with whitening was also applied to reduce the dimensionality to 1024 features per frame. Finally, the dataset was compressed from 32-bit to 8-bit data types. For the audio feature extraction pipeline, the entire video's audio track was processed in segments. It was pre-processed using the VGGS model, which was originally trained on large-scale audio dataset. The audio was first extracted from the video and converted to a log-mel spectrogram, capturing essential frequency information over time. This reduced the dimensionality of the raw audio into a compact, feature-rich representation. PCA with whitening was then applied to further reduce the feature dimension. Finally, the extracted features were quantized from 32-bit floats to 8-bit integers for efficient storage and processing. This is the real-time pipeline. The pipeline consists of two threads. The main thread is responsible for display, while the processing thread captures input from video capture device and processes it. Frames are continuously added to a queue as they come in. Every second, 4 frames are selected at 250 milliseconds interval. Once 150 frames have been collected at a rate of 4 fps, inference is performed, and the results are displayed by the main thread using the frame queue. Meanwhile, the processing of the next set of frames occurs in the second thread simultaneously. Now that we have the neural network model, how can we get it run on the GSoC available in BeagleBone AI 64? There are 2 steps for that. First, we have to optimize the model and compile it for GSoC. Then, step 3 is to deploy the optimized model onto a processor. Currently, this is in process. Hopefully, by the time you see this video, the accelerated inferencing will be fully implemented.
Here, I have run the real-time inferencing script. The processing thread starts processing the first chunk of 150 frames by considering 4 frames per second. Once the first chunk of frames is collected in the queue, inferencing is performed and the display thread displays the output frames. Currently, the frames are getting processed. The frames at the top right is post-processed. That is, when a commercial is detected, it will be blacked out and play random music of the user's choice. The frame at the bottom left is to visualize what frames are detected as commercials. During the display, the processing thread parallelly keeps on processing the next frames and adding them to the queue, so that smoothness is maintained. Here, see how the frames get blacked out when the commercial is detected and random music gets started. The user can play any content, music during this time.
The future of this project is bright. We have a working model that is able to detect commercials. We have a working input pipeline to extract audio-visual features. We have a working real-time pipeline to perform inferencing and display the results based on classification. I continue to find a solution for getting my model run on the BeagleBone AI64 accelerators. When we achieve this, we will have our first custom model that can be inferenced on the BeagleBone AI64, leveraging its onboard DSPs and accelerators. I will also focus on developing the documentation for the BeagleBone AI64 from Edge AI perspective and actively contribute to the community. GSoC has been a great learning experience for me. I am extremely grateful to everyone who was a part of this journey. I would like to thank my mentors Deepak Khatri, Abhishek Kumar, and Jason Kreiner. Every time I join a meeting with them, I learned something new. I'm very grateful to them for giving me this opportunity to work on this project. I would also like to thank the whole BeagleBoat community for their support and feedback throughout the project. It's been such a wonderful time working with the community. I'm genuinely grateful for the opportunity to collaborate with such a committed group, and I look forward to working and growing with them in the future. I would also like to thank the Google Summer of Code team for taking the wonderful initiative and giving me this opportunity to work on this project. If you find this project interesting, you can go through the links in the description to learn more about it. And if you have any suggestions or views on this project, you can share them in the comment section below. This is R. Nanda signing off.